Alright, we're going to take a look at some example problems for motion in one dimension. You're going to want to have your equation sheet out in front of you, and it's going to be a lot about determining which equation will work best with the givens and the unknowns that you have available. So I'm going to try to bring this in as close as possible so that you can see what I'm doing. Alright, so we're going to start with number 14. Number 14 asks us, if a car is traveling eastward, can its acceleration be westward? Explain your answer and use an example in your explanation. So this is number 14. So the answer is yes. If you step on the brake, then your car is accelerating in the opposite direction. So I guess instead of giving an example, I kind of put an example in my answer. If you're in a car and you're traveling forward and you throw your foot on the brake, what you're actually doing is you're causing your car to then be accelerating in the opposite direction. So, yeah, you might be moving forward still, but the acceleration is negative. Okay. So think about that one. It's kind of strange. Number 19, we have a car that accelerates uniformly from rest, that's a big key thing there, that word, rest, to a speed of 65 kilometers per hour, which I gave you in the problem is 18 meters per second, in 12 seconds. Find the distance the car travels during this time. So for number 19, let's use the guess method. So for our givens, I have V naught equals 0 kilometers per hour, which is also 0 meters per second. How do I know that's the initial velocity? Well, the car started at rest. And then it travels to a speed of 18 meters per second. And that entire time took 12 seconds. And those are our givens. Okay, so what are our unknowns? Well, I need to figure out how far did that car travel. So I'm looking for my position. I don't know what my displacement is at the end there, our change in x essentially. Okay, so I'm going to look and see what equation has initial velocity, final velocity, that's what this velocity is, and time where I can find the change in x. So if I look, I can find an equation that has the change in x equals v naught plus v divided by 2 times t. So since this is one time interval, we can use this specific equation. So then I'm going to take my numbers and plug them in. So change in x equals 0 meters per second plus 18 meters per second divided by 2 to give me the average velocity of that trip times our 12 seconds that it took to get up to 18 meters per second. So when I multiply all of that through and divide, what I end up getting is my change in x equals 108 meters. Put a box around the answer, and then... Alright, so let's take a look at 22. So in 22 we have a car that starts from rest and travels for 5 seconds with a uniform acceleration of plus 1.5 meters per second squared. The driver then applies the brakes, causing a uniform acceleration of negative 2 meters per second squared. If the brakes are applied for 3 seconds, how fast is the car going at the end of the braking period, and how far has it gone from the start? So I already wrote down our givens here. You can see that started at rest, so we know that v naught is 0 meters per second. We know that the time that it traveled during that initial acceleration, t naught, is 5 seconds. We know that the initial acceleration during that first accelerating period was plus 1.5 meters per second squared. And then for this acceleration, it was the slowing down period, so that was negative 2 meters per second squared. And the time that it was traveling at this new acceleration was 3 seconds. So what we need to do is figure out, well, what are we looking for? So we have two things we're looking for. We have A, we need the velocity at the end of the braking period. Okay, well, what else do we need? Well, we need to find, so we don't know that. We also do not know what x is. And I'm just going to drop the change in x, so I'm not going to write it from now on. So what is our final x from the start? What's our final displacement from the start? Okay, so let's take a look at part A first. The equation that we're going to need, well, I don't know. What are we trying to find here? Let's look. We're trying to find the velocity at the end of the braking period. So what do we have? We have an initial velocity, we have an acceleration, and we have a time. So we're looking at using this equation. V equals V naught plus AT. And this is one you're going to use quite frequently. So first, we need to find the velocity during the first time interval. So we got to do that first before we can find the velocity at the end of the braking period. Okay, so our solution here, our solving part, V2 equals 0 meters per second plus 1.5 meters per second squared times 5 seconds, which is what, that's an S, that's not another 5, that's a S for seconds there. So we can see that in order to find the velocity at the end of that accelerating period, we need to multiply by the 5 seconds because that's how long it's traveling at 1.5 meters per second squared. So if I multiply that through, my velocity at the end of the initial accelerating period is 7.5 meters per second. Now we need to use this equation again, where our 7.5 is now the initial, because wouldn't you agree that's now the initial velocity at the beginning of the stopping period, and the car's acceleration is negative. So I'm going to do that over here. So we're going to use the equation again. V equals V naught plus AT. So V is going to equal 7.5 meters per second. Oh, sorry, let me scoot that up a little bit. Plus negative 2 meters per second squared times, I'm running out of room, I'm a big writer, 3 seconds. Hopefully you can see that, that's 3 seconds, because that's the amount of time that we are traveling at 2 meters per second. So if I solve for that, my V equals 1.5 meters per second. So at the end of the braking period, we slowed down all the way to 1.5 meters per second. You might want to pause there, write down what you need to, make sure you can see everything. Alright, let's move on. Okay. Alright, so let's work on B. So B, we need to find x from the start. First, we need to find the first interval distance. Okay, so let's draw a little picture. So we have this distance x here. We'll call it x1. Then we have this distance x2. And this is where the acceleration was plus 1.5 meters per second squared. And this was when the acceleration was negative 2 meters per second squared. Even though we were traveling at a negative acceleration there, we still were traveling. So we were still moving some distance. So we still had some displacement happening. So what do we need to do here? Well, we're going to use this equation, x equals v naught t plus 1/2 at squared, because we have v naught, we have t, we know our acceleration. That will allow us to find that displacement, that final displacement. So let's plug in our numbers. So x equals 0 meters per second times 5 seconds that it traveled, plus 1/2 times plus 1.5 meters per second squared times our 5 seconds, and we're going to make sure that we square that 5 seconds at the end. So after we plug all of that in, we get x equals 18.75 meters. So that's our initial x1 part. So let's label this all x1 so we know that was this distance here. Okay. So now we need to find that segment of x2. So let's find x2, that second distance there. So our equation is again x2 equals v naught t plus 1/2 at squared. And this time we're looking at that second segment where we were beginning to slow down. So that means our v naught is 7.5 meters per second. And the amount of time traveling while we were slowing down is 3 seconds. And then our acceleration was negative 2 meters per second squared. And again, that was at 3 seconds, and we need to square those seconds on the end there. So now we can go ahead and plug everything in. So we get x2 equals 7 point, oops, sorry. We'll just do this. You already plugged everything in. I'm just trying to get the solution, just kidding. So I end up with 13.50 meters. And so that's that second distance. But if I want to know how far we traveled from the start, I need to add those two together. So the actual answer would be the distance, let me make sure you can see what I'm doing, from the start. And that's going to be 18.75 meters plus my 13.25 meters. And that gives me 32.25 meters, and that is your final answer there. All right, not too bad. That one wasn't too difficult. All right, let's take a look at number 26. Let me move this up so we can see better. Number 26. We are looking at a ball that's thrown vertically. So first I'm going to draw a little picture, and then we'll write down our answers to A through E. So if I were to take a ball and throw it up, let's say from my left hand to my right hand, we would end up with a parabola shape, something like this. Let's pretend like it's perfectly even and perfectly drawn. And as that ball goes up, some interesting things happen. As soon as it's released from my hand, gravity takes over. Okay, and as gravity takes over, it actually begins to slow down on the way up. Okay, so let's say that I throw it at 40 meters per second. It slows down this entire way to the top. So the velocity slows down. Okay, so the velocity is decreasing all the way to the top there. So much so that at the very top, at the center, our velocity equals 0 meters per second. So we actually have no velocity at the very top. Okay, then after it hits that 0 velocity on the way down, it speeds up. Velocity increases. And it's going to slow down by 9.81 meters per second every second. It's going to speed up by the same over here, 9.8 meters per second every second, meters per second every second, and then it's going to actually hit my hand as long as it's at the same height at 40 meters per second. So I throw it up with 40 meters per second of velocity. It hits my hand as long as my hands are at the same height at 40 meters per second. Velocity at the top is 0. Okay, well what about the acceleration during this entire time? What does the acceleration due to? It's due to gravity. So the entire time my acceleration is 9.8 meters per second squared, no matter where I'm at. If I'm here, the acceleration is 9.8 meters per second squared. If I'm here, even if I'm right at the top, acceleration is still 9.8 meters per second squared. Here, here, here. No matter where I'm at on that graph, the acceleration is always 9.8 meters per second squared. And it's always pushing downward because that's where gravity is pushing. Okay, so now I think we can answer those questions. So let's take a look at those questions. I'll go over here so we have some room. So A says, what happens to the ball's velocity while it is in the air? So it decreases, becomes 0 at max altitude, and then increases in the negative direction. So we're going to put decreases, becomes, let's make sure you can see me, it's rolling up over there, becomes 0 at max altitude, then increases in the negative direction. And we could see that from our drawing, that that's what's happening. Okay? Perfect. What about B? At B, what is the velocity when it reaches maximum altitude? Well, we just talked about that. It is 0 meters per second. All right, what about C? What is its acceleration when it reaches the maximum altitude? Well, I told you that acceleration during this entire thing is 9.8 meters per second squared, so that's what it is there. All right, what is the acceleration right before it hits the ground? Still, it's 9.8 meters per second squared. That isn't going to change. It's the same. Sorry, so you can see a little better. Okay, what about E? Does its acceleration increase, decrease, or remain constant? I just told you that acceleration is going to remain constant. It's going to be due to gravity, and it's going to be 9.8 meters per second squared. And it seems kind of strange, but that's what happens when you throw a ball straight up in the air. Now let's look at number 30. So in number 30, we have a worker that drops a wrench from the top of a tower 80 meters tall. What is the velocity when the wrench strikes the ground? So I drew a little diagram, and I think it's best to do that whenever you can. And I have, this is my wrench, don't make fun of it. And then this is the that X of the building, and because this wrench is falling, that X is negative, so that's negative 80 meters. And the velocity, the initial velocity of anything that's dropped during free fall, if I'm holding it out and I drop it, that initial velocity is 0 meters per second. And that kind of trips people out because it's not stated, but it's something you just need to know. Okay, so let's write down our givens. So we have V naught equals 0 meters per second because we're dropping that wrench from rest. Our position is negative 80 meters, and our acceleration is negative 9.8 meters per second squared. So what are we looking for then? Well, oops, wrong thing. What is our unknown? We are looking for v. What is our final velocity at the end of that drop? Okay, so this is a little different. I don't have time, so I can't use v equals v naught plus at. But I do have my change in x this time, which is x. And remember, we don't always write the change there. And so if I know that, then I can use this equation here. V squared equals v naught squared plus 2a change in x, or x. Okay, so now all I need to do is plug everything in. I don't know v, so I'm looking for that. I do know my initial is 0 meters per second, and I'm just going to square that, so obviously that's going to become 0 plus 2 times negative 9.8 meters per second squared times negative 80 meters. And my rounding might be a little bit off because I used 9.81 before, but on the AP test you're going to use 9.8. But it won't really matter that much. That's going to be minuscule. So anyways, after you do that, you get v squared equals 1,569.6. I got to take the square root, so I'm going to take the square root of that on both sides. And so then what I get for my solution is v equals negative 39.62 meters per second squared. And now you can't get a negative out of that square root, but we know that it is falling in the negative direction, so that velocity is in fact negative. So keep that in mind. Okay, let's look at 31. So 30 was pretty easy. Let's check out 31, make sure you can see it. So in 31, we have a peregrine falcon that dives at a pigeon. The falcon starts downward from rest with free fall acceleration. If the pigeon is 76 meters below the initial position of the falcon, how long does the falcon take to reach the pigeon? We're going to assume that the pigeon remains at rest, so the pigeon isn't moving. Okay, so let's write down our givens. So I know that v naught equals 0 meters per second. I know that x in this case is negative 76 meters. And I know that the acceleration is due to gravity at negative 9.8 meters per second squared. Okay? So far so good. We could draw ourselves a picture. And I can't really draw a bird very well, but I'll try. So here's my bird. Here's his little head. He's the falcon. He looks like the pigeon. I actually really like birds, so I'm not doing him justice. But here, this is the falcon. Okay, and down below we have the pigeon, so here's the pigeon. He's a little easier to draw. There's my pigeon. I'm not an artist. We can see this, and that's okay. So he's going to dive down below to him, and so my x is equal to negative 76 meters per second. That's negative. Let's move that. Okay, and I know again that the v naught is 0. And then I know that all of this is happening because of acceleration, so it's 9.8 meters per second squared for A. Okay, so now that I've drawn a disastrous picture, let's look at the unknown. So again, I'm looking for my velocity. Oh, nope, I'm looking at the last question. Just kidding. I'm actually looking this time for time. And so there's two ways you could do this. Okay, looking for time this time. My bad. I'm sorry. I apologize. So two ways. I'm going to show you both. Okay, so the first way is we could use this equation, x equals v naught t plus 1/2 at squared. That's the first way. The other way is we could use v squared equals v naught squared plus 2a change in x. So either would work. Let's take a look at this one first. So we would plug everything in and we get negative 76 meters equals 0 times t plus 1/2 times negative 9.8 meters per second squared. I'm running out of room, so I'm just going to write it down here. And that's the t squared. Really, here, let me just scoot this over a little bit so that I have enough room. I'm such a big writer. I'm really sorry. I apologize. I try to write smaller, but it just doesn't happen. So that's t squared over there. So if I solve, I end up getting this 76 meters equals negative 4.905 t squared, and then I can divide both sides by 4.905, negative 4.905, and then I end up getting 15.49 equals t squared. Okay, and then of course I'm going to take the square root of both sides, and so when I do that, I get time equals 3.94 seconds. So that would work. Okay, pause it, do what you need to do. On this side, same thing, plug everything in. So v squared equals 0 meters per second squared plus 2 times negative 9.8 meters per second squared times negative 76 meters. So when I do this, I get 1491.12. It's a 9. It's a terrible 9. And after I take the square root, I get negative 38.62 meters per second. So I have the velocity there at the end. Well, then I could plug that into acceleration equals change in velocity divided by the change in time. And with that, I would get negative 9.8 meters per second squared equals negative 38.62 meters per second. Make sure you can see what I'm doing. And that is divided by the change in time. So once I flip that all around, I get the change in time equals negative 38.62 meters per second divided by negative 9.8 meters per second squared. And sure enough, it gives us the same thing. The change in t equals 3.94 seconds. So there's usually, typically more than one way to solve a problem correctly in physics, which can be frustrating. So that's two ways to find time in this case. Let's box our answers, as always. And hopefully you're doing okay. Okay, we're looking at number 40. We have a small fish dropped by a pelican that is rising steadily at 0.5 meters per second. We need to A, figure out after 2.5 seconds what is the velocity of the fish, and B, how far below the pelican is the fish after 2.5 seconds. So let's start with what do we know, right? We always got to start with our givens. What's given in the problem? We know the velocity of the fish. I'm just going to do it like this. Little fish. It's adorable, I know. 0 meters per second because he's in free fall, so he did not have a velocity to begin with initially. We know the speed of my pelican, which is 0.50 meters per second. And then I know the time at which the fish has fallen, which is 2.5 seconds later that we're looking at. Okay, so we have two things that we're trying to figure out, and that would be, make sure you can see, that would be A, what is our velocity of the fish, and B, what is our position of that pelican, or how far below that pelican is the fish after 2.5 seconds. So those are the two things that we will be looking for. Okay, and actually I think we need to change this. We're not looking for the final position of the pelican, we're looking for the final position of our fish. Okay, so my bad, that was wrong, but now you got the right one. Okay, so I drew a little picture. Here's my pelican. He's a little better than the peregrine falcon, but still pretty bad. And here's my fish, and it falls, and after 2.5 seconds, we're going to try to figure out what's the velocity of the fish, what's the position of the fish compared to that pelican. So let's go for the equations, shall we? Let's take a look at the equations. I'm going to write them over here. So I'm going to use, for the first one, V equals V naught plus AT to help me find out what is our velocity at the end for that fish, which makes sense. We have time, we have initial velocity, we know the acceleration. Oh, which we didn't write down here. Let's write that down too. Acceleration is what? It's 9.8 meters per second squared because we're talking about free fall. So that is something I did forget to write down, in fact, but now we have it. Okay, so what is our other equation for part B? We're looking at using x equals v naught plus v over 2 times t. Okay, so let's take a look at our plugging our numbers in for A. So for A, we're going to do, you know what, I'm going to move this over a little bit so I have some room because we know I write too big. So A, let's make sure you can see it, yes. A is V of the fish equals 0 meters per second plus negative 9.8 meters per second squared times the 2.5 seconds that fish was in fact in the air. And so that gives me a final solution of a velocity of the fish equals negative sorry about that, negative 24.53 meters per second. Okay, put a box around my answer. Beautiful. I have my answer to part A. Okay, what about B? Let's take a look at B. So for B, I'm going to do x equals 0 meters per second plus negative 24.53. Now that I found that from the previous problem, so I needed to do that previous problem in order to get this one done. Sorry, I don't know what's going on right there with my 4, like so. I'm going to divide that by 2 and then multiply that by 2.5 seconds. And so my final position is negative 30 meters. But that's not the final answer for the position because we want to know how far below the pelican is the fish after 2.5 seconds, and there's something interesting happening because we know that the pelican, he's still moving. So we need to use that information. So let's write that down. So, but the pelican is still moving. So we need to figure out how far has he gone to. So we're going to use this distance equals velocity times time. So the x of the pelican is going to be 0.5 meters per second times the 2.5 seconds. And that gives us 1.25 meters. So to find the final x of our fish, we need to actually do the pelican's position minus the x of that fish initially. Okay, so we'll take our 1.25 meters and we're going to subtract our negative 30 meters, and so then we end up actually adding those two together. So my final position of the fish equals 31.25 meters. Okay, box that up. That's my final answer for B. Okay, here's B. A was up there at the top. Nothing too difficult. Just getting some used to writing these problems, solving these problems, looking for the right equation, And you can do this though. You've got this. You can absolutely do this. And I have faith in you. So let's look at one more for today. We're going to look at number 45. Okay. And in number 45, we have a tennis ball with a velocity at 10 meters per second to the right is thrown perpendicularly at a wall. After striking the wall rebounds in the opposite direction with a velocity of -8 meters per second to the left. If the ball is in contact with the wall for 0.012 seconds, what is the average acceleration of the ball while it's in contact with the wall? Okay. I'm going to skip out on the diagram on this one, but if you would like to draw it, you may. So I know that my initial velocity is 10 meters per second. Sorry, because that is what that ball starts out with. Its initial velocity is -8 meters per second, and the time is 0.012 seconds that it comes into contact with the wall. So what are we looking for? Well, we're looking for the average. Sorry, that A was already there and it screwed me up. The average acceleration. And so what do I need to use? Well, we have this handy dandy equation that says V equals V naught plus AT, and that is solving for average acceleration. So now we just need to switch it around and solve for A. So one of the big things that I find is hard in AP for some of you is that you haven't had algebra in so long you don't remember how to manipulate variables, and that becomes an issue. So if that's one of your issues, you need to come see me at some point. Maybe we can set up a day and I can just sit with you and we can wear masks 6 feet apart, and I can show you on the board how to manipulate the variables, because that's going to become very important. So if I plug this in, that's rearranging the equation around, I get, let me make sure you can see me, pull it up a little bit. A equals -8 meters per second minus 10 meters per second, all divided by 0.012 seconds. And so what do I get for that at the final? Acceleration equals -1500 meters per second squared, which seems rather large, but it can happen with a ball easily. Okay, so that concludes our example problems for today. There may be more in the time coming, but that's what you are to work on for today. And I'm going to open up the online Lon Kappa homework, and we'll be working on that in the next couple of days. Okay, thanks.